one substitute in, right? And for second order, don't forget, you have to do 2 times. Okay, for this one, okay, you have to do 2 times. And I don't have to show you step by step, okay, because all those are being uploaded. Okay, I just want to highlight, okay, something you need to pay attention. Many of students are not able to capture this one. And this one, most of the students have no problem to do the digital part, which means to convert the actually, I don't know why the student use hide the answers. I'm not sure whether he's so interested in the module or so in what. So, first thing, I think most of the students have no problem to convert the S function to a differential equation and do the approximation. After you get this one, then this is your difference equations, right? To approximate the ds. Okay? And if you still remember, this is a linear control plan. So what we have done, we have represented the ds into difference equation, right? Then my GS here continuous plan. This one should not count. Okay? Don't count this one. Okay, count this one. After you count this one, what you have to do actually, this one is a question from text. So what you have to do, you can use a MATLAB to simulate. Right? Because in your MATLAB you can simulate a transfer function. Then based on the transfer function, you get your output. Okay, then they're using the zero order mode, okay, to the plan. Then you can simulate, okay, how is the time response. Okay. Okay, so first of all, this one I'm going to highlight 2 things. So one you are going to digitize, or you are going to find out the difference equation is for the digital controller part. Okay, so digitize your GF. And secondly, after you obtain the controller, digital controller, you can apply your MATLAB code simulator, MATLAB simulations, okay, to estimate how its output is going. And for week 3, most of the students also got the correct answer. For this one, actually, we have introduced during the lecture. So for those who have a problem, you can refer to week 3 and week 4. Week 4 lecture slide. Just follow. But as I mentioned, for all these things, usually the tricky part for the student. First of all, I believe all of you know how to apply the definition of the data flow, right? Then the tricky part for some students may not be able to get the answer is you don't know how to do summation. So you will see most of the time you will have something called the geometric series. So this one is also a geometric series, right? Right. Where your base is half of that one. Then if this one is less than 1, your infinite summation will be 1 over 1 minus a. Where is a? A is your r multiplied with z of x1. And for the second one, for the stability, after you calculate all the roots, you should check about magnitude. Okay, and the magnitude, if it's less than 1, is stable. If it's greater or equal, even equal to 1, the DIPO is unstable. Okay? The signal itself is at a constant value or marginally stable oscillating. The signal itself, but the system will be di/dt. Okay. For question 4, for exercise 4, many students got difficulty to do this. And this one, they need some of the math tricks. Okay, they need some tricks from the math. Because for k value less than 0 is 0, so we can do the initial condition for 0. So what we are going to have, if k equal to 0, what we get? We get 0. If k equal to 1, what do we get? We get t multiplied with z power minus 1. If it's k equal to 2, what I get? We get 2t z power minus 2. If we have 3t, if we k equal to 3, we get 3t z power minus 3. That's so straightforward. And how to do this summation? Is this one a geometric series? No, right? But your target is to make it be a geometric series, right? That's how. You will notice this one keep increasing, every time increase by 1, right? Because your k increase. So if you think if I'm able to shift, if I'm able to come out something else, you can see I come out this one dt, therefore minus 3. If this one I have something like 2t, therefore minus 3. Then use this one minus this one, am I able to get, because my target is to get something impossible, I want to have something like this. If I'm able to get this one, which is a unique geometric series, are you able to get the summation? Yes, right. So in order to get this one, I need to do something from this one to get this one. So notice in order to get this one, I want to have something like this. And how can we get something like this? If I multiply with, if we multiply this Ez with E with Z, what do I get? This one get 0. Then minus 1, right? Then this one I get. This one multiplied with Z power minus 1, I get this one, right? In this one multiplied with Z power minus 1, I get this one, right? So I get all this, right? So now if I'm using this one minus this one, so I get what I want. So for this one, I'm able to calculate the summation. Yes or no? Yes, right? That's not no. Okay, this one. Then please relate it here. And this one is 1 minus z power minus 1 multiplied with your Ez, right? Then your Ez will be is that right? So far for all the 4 exercises, I find only this one slightly okay, because you get to learn some of the mathematics. But as an engineer or future engineer, you should have this kind of thing. Because you know what is something you may be able to get solution. You want this one, right? not this one. What's the difference between this one and this one? What's the difference between this one and this one? The difference is this one. And this one actually is complete octet, but this one I must have it same form as one. Right? And for the second one, I think we spent 1 hour last week, right? So you can either have some answer like this, or you can have some answer.
It's only sketch.
So you can have some answer like this. If your pole is here, it's the outer one. If your pole is inside, you will get this one. Okay, if your pole is at the inside, you need to curl like this, you get this one. And so on and so forth. Okay? Or or you can combine just all the things. Another one is you can combine all this with something, okay, not included in the class code notes, but in my slides, which basically is a digital one for this slide. Okay, but we have digital one, right? The unit circle. Basically, that one is just a summary. It's just a summary of corresponding input-output response at the corresponding locations. Okay, actually the question I want to go through is so I saw students got two type of solutions. Both are okay. What we do. One is, remember the unit forward and backwards. So this is the definition of the forward, remember. Right? And what the student do is, for this one, is basically the differentiation. And differentiation is met with your S operator. Right? Then for this one, you can just put a. So for this one, you can consider as S, Y, S. For this one, if you do the Z transform, what you get? You will get your YZ. Z minus 1 divided by. And if your ys is eventually going to map with your yz, right? Then your S operator can map with Z minus 1. Okay? This is going to be a very simple thing. Okay? And similarly for the backward and trapezoidal, can do similar ways. Okay, I think this one I have scanned and upload to the Moodle. And I also saw another submission. On the students. For example, for the forward, what the student did, they use the integration. So for the integration, you do the Z transform. So this is a forward method, forward rectangular for the integration. As I mentioned, the integration rectangular and your Euler's back over again there. Right. So if they do the Z transform of both, so this one you have to do the Z transform UK, and this one you have to do the Z transform UK minus 1 and then UK minus 1. So what you get? You get UZ, and you get UZ multiplied with Z power minus 1, and T times EZ multiplied with Z power minus 1. So you put UZ and TZ on one side, you get UZ multiplied with Z minus 1 is equal to T equal to T times EZ. Right? Means both left and the right you multiply with Z. So you get this. So you see what's the difference between these two? What's the difference between these two? The answer is this one. This one is flip over, right? Why flip over? Because this one is your integration, output divided by input integration. If you want to find out the differentiation, what you need to do? You need to flip over. Right? So your EZ over your UZ. Okay. And the other one you should do for the backward. Okay. You get the expression for the backward. Then you do the backward. Okay. This one is follow the definition. This one follow the definition. This one follow the formula. Right? This one basically you use the definition, you can derive the property. The property is your time delay will be converted to Z power minus 1. Your left shift will be past 1. Okay? So this is the thing I want to highlight. Okay, usually for the Z transform you got two ways to use it. One is you apply the definition. Right? But when you apply the definition, there are also some slightly tricky part. How to get your delay out? You need to shift your variable. Okay, you need to shift your variable by 1 time, 2 times. Then you're able to get this one. And basically, you see, for the definition, you get this one, and this one use a property here. This one and this one in the same way. Right? They use the same way. Because this is how they divide the definition, and this is how they divide the answer. Okay, and we are going to learn and apply this one 2 weeks later. Okay? I should know where they come from. Okay, so that's all for today.